Hello everyone. Today we're going to do solve one of the homeworks from chapter 5 on op-amps. As I mentioned, the analysis for circuits including op-amps is similar to what we have been doing so far, and we're going to follow the three-step universal approach. The only difference is that now we're using a new component, the op-amp, and therefore there's a new equation to be used for that component. If the op-amp is assumed to be ideal, that equation basically tells you that the voltage of the potential of the positive and the negative terminals are equal to each other, assuming that there's a negative feedback in the system, or in other words the circuit is stable, and also the currents that are going into the positive and negative terminal are zero. And that's the assumption for this specific problem that we're going to do right now, and therefore we're going to use the equations as given. Okay, we're going to start the process by labeling the circuit. So this is, we're going to start by identifying the nodes first. These are the nodes. And we're going to move on to labeling the voltages. So this is our 0 volt that's given. This is 15, 10. This is already labeled as Vout2. This is labeled as Vout1. This one is labeled as Vout2. So the only two nodes that are not labeled is this one and this one. Now I'm going to use the equation for the components at the time of labeling, and actually call this label 15 and call this one 10, because we know these two are equal to each other and these two are equal to each other. With that, we move on to the currents. So there's a current for this component. I'm going to call that current I1. There's a current coming out of this one, that's also I1. Since this current is 0, there's no current here, obviously. It's not connected to anything, so these two currents are equal to each other. There is no current here, as we know. There is no current here, again, as we know. I'm going to call this current I2. Call this one I3. And there is a current here, and call that I4. And there's a current here, I'm going to call that I5. Current here, and call that I6. And this would be 0. This is 0. And that concludes our labeling. So if you notice, all nodes have a voltage name or label, and all components have a current label. Now we're going to move on to writing equations. So KCL, I start with KCL. There is no KCL to be written for this node, Vout1. We already wrote the KCL. For this node, we're going to, for the 15 volt node, we're going to write the KCL. So the current I1 is going in, and I2 and I3 are leaving the node. So I2 and 3 leaving, I1 is going in, and this current is 0. I1 is equal to I2 plus I3. For the node Vout, I2 is going in, I6 is going in, and I4 is leaving. So I2 plus I6 is equal to I4. For the 10 volt node, I4 is going in, I3 is going in, and I5 is leaving, and this current is actually 0. So I3 plus I4 is equal to I5. Sorry, I5. So now equations for components. So we have total of 1, 2, 3, 4, 5, 6, 7 components. We already wrote the equations for the op-amp, so equations for the resistors are left. So for the 500 ohm, I1 is equal to Vout1 minus 15 divided by the resistance value. I'm going to use the values in kilo ohm, and the currents would be in milliamp. For the 2K resistor, I2 is equal to 15 minus Vout2 divided by 2. For the 400 ohm, or for the 5K, I3 would be 15 minus 10 divided by 5. So let's look at this. For the 5K resistor, on one end you have the 15 volts, and the other end you have the 10 volts. And that actually gives you a value of 1 milliamp immediately. So for I4, the current of 400 ohm, you have Vout2 minus 10 divided by 0.4. And finally for I5, you have 10 minus 0 divided by 1. That immediately gives you 10 milliamp. So as you notice, there is no equation for I6 or I1 in this circuit, the currents that are going out of the op-amps, and that's fine. You don't have to have equations for all the currents in the circuit. You have to write equations for the components, not the currents. So now we're going to move on and use the current equations in a set of equations for components, and put them in the KCL here and complete the process. So I1, we now, from the equation for components, we know it, that's Vout1 minus 15 and divided by 0.5 is equal to I2, which is 15 minus Vout2 divided by 2 plus I3, which is 1. And from this equation, I3, which is 1, plus Vout2 minus 10 divided by 0.4 is equal to I5, which is 10 milliamp. So now from this equation I can immediately calculate Vout2. So Vout2 minus 10 is equal to 9 times 0.4, that's 3.6. In other words, Vout2 is equal to 13.6 volts. Now, with this known, now I can put this back into this equation up here and calculate Vout1. So Vout1 minus 15 divided by 0.5 is equal to 15 minus 13.6 is 1.4 divided by 2 is 0.7 plus 1, and therefore V out 1 is equal to 15.85 volts. Now with these two values, I can put them back into these equations for components and calculate all the remaining current values that are unknown. I'm going to leave that to you. Hope this has been helpful, and thank you for your attention.